Welcome to Hartman Math. This is lesson 3.5, Exponential and Logarithmic Models. We're going to focus on the exponential model. So we got exponential growth, exponential decay. We're doing it in terms of the natural base e, y equals a times e to the bx. So that's growth when b is greater than 0. And then decay, a times e to the negative bx, also with the positive b value. So example number 3, radioactive iodine has a half-life, so we're looking at a half-life problem, of 60 days. How long will it take to decay until 20% remains? So we want to focus on the half-life part first. Essentially, we want to get the decay rate from that. So the 20% does not pertain at the beginning of the problem. We want to focus on the half-life. Okay? And we're talking about half-life. This is a decay problem. Now, earlier in this unit, we did have a formula for half-life. We're going to now use the more generic exponential decay model. Okay? And even if you forgot the negative and did it as a growth, it really wouldn't matter because we would just get b to be negative anyways. So either one of the formulas really works. But we're going to focus on the half-life. We are going to say that we start with a, and then 60 days later, how much are we going to have? Well, half-life means we're going to have half as much. So if we start with a, we're going to wind up with half of a. And we know x to be the 60. What we're going to go after is the b. So our next step is to divide both sides by a. Now we're going to rewrite this from exponential form into log form. Since we're talking about log base e, that's the natural log. Divide both sides by negative 60. That's our exact value for b. And then we're going to do some intermediate rounding in this part, which means we're going to round off b, and then we'll also use that. And when we do so, we want to go with 4 significant digits. Okay? Leading zeros don't count. So basically, the first digit that we see that's non-zero, that starts the count. That's the first. And we go to 4, a total of 4 significant digits. So in this case, the 0 does not count. b is about 0.01155. There's our 4 significant digits. Any leading zeros do not count. Zeros in the middle do count. So if it had been 1055, that 0 still counts, but zeros at the beginning do not count. So we found b. Now we're going to go after the a. And we can go after our problem here. So how long does it take to decay until 20% remains? So be very careful about the wording of the problem, because it might say until 20% decays away. And it is all about what we have remaining. So if it says 20% decays away, then we would have 80% remaining. In this case, we have 20% remaining. So 20% of a, our starting amount, is approximately, because we've already rounded, a times e to the b, negative b, we just found b, times our unknown x. Because now we're saying how long will it take? X is our time in this case. So now x is our variable. Once again, divide both sides by a. The solve process is going to be very similar. Rewrite it as a log, in this case a natural log. Divide by the negative b. And I think we're going to get about 139 days. All right, example 3 also, kind of a second example 3. Similar type situation. A research experiment, a population of bacteria. So if you are kind of hardcore biotech, you might raise your hand and say, the data here is probably inaccurate. It might be. Okay, so we're just kind of working through how we would solve the mathematics of it. Not necessarily saying this is a realistic scientific expectation. We are talking about exponential growth. After 3 hours, there's 420 bacteria, and after 7 hours, there's 680. How much is there going to be after 10? So each of these data points is going to generate an equation. We're talking about exponential growth. So it kind of creates a system there. A system, we have two unknowns. A and B are unknowns. And you can list them in either order. I usually prefer the time that's further down the road. So the 7 hours I did first, and then the 3 hours I did second. And one thing we could do, there's different ways that we could solve. But we could take these two equations, and then we could just kind of divide them in this stack. So this divided by this equals this divided by this. If we do so, over on the right, the a's cancel, and e to the 7b divided by e to the 3b. That observes the exponent properties that we know of. That's e to the 4b. And if you felt like canceling and reducing, you could, but it's not really necessary. Because now we're going to rewrite this as a log, so natural log. And then take that result and divide by 4. And again, 4 significant digits. B is about 0.1205. It would be 4 significant digits. And then from there, we need to solve for A. So we can go either one of these equations, it wouldn't matter which, and we replace B, and now we're going to solve for A. So this is just a number. E to this power is just a number. And we're talking about A times this, so we're just going to divide both sides by this number. 420 divided by E to that power. And you get, it's about 292.6. Again, that's rounded to 4 significant digits. Now, if the question was, how many bacteria did we start with? You definitely wouldn't answer this way. You would probably say something like maybe 293. We definitely can't start with 0.6 of bacteria. But it's good for our model. So we can use it in the model. It's just not necessarily an answer. How many will there be after 10 hours? So starting amount, e to the, there's our function. If we want to know for 10, we can just substitute in the 10. If we do that, we do that calculation. If we go to the nearest bacteria, we're going to go 976. But you might have noticed in the original problem, because I think it's maybe difficult to count individual bacteria, it's more likely that we might round to 100, or in this case 10. It might be more appropriate to say 980 bacteria. That's it for today. I'll see you next time.